Right, welcome everybody to the set theory seminar of the CUNY Graduate Center. So today we have Daniel Hathaway from the University of Vermont, and he's going to speak about sigma to 1 UB absoluteness between V and HOD.
Okay,
Right.
thank you so much for this opportunity. So I just want to mention this is joint work between Gabriel Goldberg and me. So yeah, I want to start with some background. So first, let's talk about what is a universally bare set of reals. And by the way, when I talk about a set of reals, I'm usually talking about a subset of actually. But anyway, let kappa be an ordinal. We say that a set of reals A is less than kappa universally bare if and only if there are set size trees T plus and T minus on omega cross ord, such that the set of reals is the projection of the first tree, and moreover, the two trees project to complements in any forcing extension of size less than kappa. This is usually called kappa universally bare, but I'm calling it less than kappa universally bare just to be clear. And the collection of all universally bare sets of reals is often called gamma infinity, but we will just call it UB. Okay, so yeah, a set of reals is universally bare if and only if it's less than kappa universally bare for every ordinal kappa. And so to be less than kappa universally bare, we have to consider all forcing extensions by posetsets of size less than kappa. But it turns out that you only need to consider one of them. So a set of reals turns out to be less than or equal to kappa universally bare if and only if there is some generic for the call omega kappa forcing such that you have trees T plus and T minus that project to complements in that forcing extension. And the set of reals is the projection of the first tree. Okay, and by less than or equal to kappa universally bare, I mean, I'm talking about posetsets of size less than or equal to kappa. Okay, so this is kind of a clever trick we're going to use a couple times. So instead of having to consider all forcing extensions of V to show that a set is less than or equal to kappa universally bare, all we have to do is consider this particular, one particular generic for this particular forcing. And then we have a key result. Let's call this L of AR absoluteness. This is due to Wooden. It says, sorry, I got to move these faces out of the way. Assume there's a proper class of Wooden cardinals. Let G be generic over V, and let A be a set of reals that's universally bare. Well, in the forcing extension, you can reinterpret A, and we usually call the reinterpretation A star. And what Wooden's theorem says is that there's an elementary embedding of L of AR into L of A star R as computed in the forcing extension. So there's this elementary embedding of the first L of A model to the second L of AR model. And moreover, this elementary embedding maps A to its canonical reinterpretation A star. You know, a simple example of this would, if you have a proper class of Wooden cardinals, then you cannot change the theory of L of R by set size forcing. One thing interesting about this is the hypothesis that there's a proper class of Wooden cardinals can be replaced by a hypothesis on the closure of the UB sets of reals. Specifically, Wooden shows that if the UB sets of reals are closed under sharps, scales, and projections, then you get the conclusion of his theorem. And this is discussed in his paper, Suitable Extender Models 1. And closure under sharps means for every set of reals B that's universally bare, the set of reals B, R sharp exists and is universally bare. Closure under projections means if you have any set B which is universally bare, then every set projective in B is universally bare. And closure under scale means for every universally bare set B, there is a scale for B which is universally bare. So recall that a scale for a set of reals can itself be coded as a set of reals. And I'm just going to make that identification. So whenever I have a set of reals and I talk about a scale for the set of reals, that scale, I'm just going to say, is literally a set of reals. Okay, so what are sigma 21 UB statements? Well, a sigma 21 UB statement is a statement of the form there exists a universally bare set of reals A such that some projective statement is true using A as a parameter. And the way I represent a projective statement is I talk about the model H omega 1 comma A satisfying a first order statement. Okay, so sigma 21 UB statement is there exists a UB set of reals such that some projective statement holds. We can also talk about these formulas, but allowing real numbers of parameters or even sets of real numbers as parameters. And there's a very natural and important example of a sigma 21 UB statement, which is namely the statement that there exists a mouse satisfying some statement. So for example, the statement there exists a countable pre-mouse M with a super strong cardinal, for example, and there exists a universally bare omega 1 iteration strategy for that pre-mouse. That whole thing is a sigma 21 UB statement. Okay, so lots of mouse existence principles literally are sigma 21 UB statements. And we have this very interesting theorem of Wooden that says, assuming you have a proper class of Wooden cardinals, then sigma 21 UB statements are absolute between V and its set forcing extensions. So for the upward direction, that just uses L of AR absoluteness, because if you have a universally bare witness for a sigma 21 UB statement and you do some forcing, if you reinterpret the UB set in the extension, then you have an elementary embedding of the original L of AR model to the L of A star R model. And so that gives you that the extension, in the extension, A star witnesses the same sigma 21 UB statement. Okay, so that's one direction. The upward direction is by L of AR absoluteness. The downward direction is more complicated. I'm not going to really talk about that, but I claim that can be shown using the stationary tower forcing. So if you do a forcing, and then in the extension, there's some UB set A, which satisfies a sigma 21 UB statement, then somehow using stationary tower forcing, you can pull back B into the ground model, or like get some kind of replacement for B that ends up working. So a little bit of, so one would have to do a little argument there to get that to work quite right. Okay, so if there's a proper class of Wooden cardinals, then sigma 21 UB statements cannot be changed by forcing. And the main topic of this talk is, are sigma 21 UB statements absolute between V and HOD? So you might wonder, why would we even suspect absoluteness, sigma 21 UB absoluteness between V and HOD? Well, it has to do with the previous slide, because of, well, Vopenka's theorem says every set is generic over HOD. So if that was a little bit stronger, if V itself was a forcing extension of HOD, and V had a proper class of Wooden cardinals, then HOD would have a proper class of Wooden cardinals as well. And because of generic absoluteness of sigma 21 UB statements, you would have V and HOD agree on sigma 21 UB statements. Okay, so literally, if V was a forcing extension of HOD, then the previous slide would give us what we want. Unfortunately, V is not necessarily a forcing extension of HOD, but you do have this partial result of Vopenka's theorem that every set is generic over HOD. So maybe you could take all these forcing extensions of HOD, somehow put them together, right? So it seems plausible that we might have sigma 21 UB absoluteness between V and HOD. I think I'm going to use this later, but it's also interesting in its own right. There's an extension of Vopenka's theorem. I think perhaps this is folklore, which says if you force over V by an OD homogeneous forcing, then every set in the extension is generic over the HOD of V. So certainly every set in the extension is generic over the HOD of the extension, but in this situation, the HOD of the extension is a ground of V, so somehow you can get every set in the extension generic over the HOD of V. Okay, so it's kind of an interesting improvement there. Oops, too much. Here's a very crude description of the situation between V and HOD in terms of this absoluteness. If both V and HOD have a proper class of Wooden cardinals, then sigma 21 UB statements are absolute between V and HOD. but that's a little bit strange. Like, why do they both have to have a proper class of wooden cardinals? The upward direction, that's the easier direction. It only uses that HOD has a proper class of wooden cardinals. The downward direction is more complicated. That's what Gabe and my theorem addresses. So the downward direction relies on V having a proper class of wooden cardinals. And then there's this question of, can you get the downward direction using certain parameters? And this turns out to be somewhat complicated. So I'm going to address that at some point. Okay, so I want to start talking about the upward direction from HOD to V. So if a sigma 2 1 UB statement holds in HOD, and HOD has a proper class of wooden cardinals, then I want to show that V also satisfies the same sigma 2 1 UB statement. So here's a lemma which is useful for that, but it's also just useful in general. It says, if you have any set of reals A which is universally bare in HOD, then its canonical interpretation to V is universally bare. And maybe I should go through the proof a little bit. I don't want to spend a whole lot of time on the details, but just give an indication of what's going on. So, we have this A, which is universally bare in HOD. And by A star...
sorry, Dan,
yeah,
can I just add? So you're not assuming that V is a forcing extension of HOD here, right?
That's right.
So by A star, you just mean the projection of a tree witnessing.
Well, not just one tree, but all trees.
Okay.
So if you look at all trees in HOD that project to A,
right?
And you take their projections in V and union them together. That's what I mean by A star.
I see. Okay, so basically the same definition that you would use if it were a forcing extension.
Yeah, exactly.
Yeah, okay.
So we're patching together all these trees.
Mm-hmm.
So how does this theorem work? We have this A, which is universally bare in HOD, and we let A star be that canonical reinterpretation that we just talked about. Hold on, the faces are blocking. So let K be an arbitrary ordinal. We want to show that A is less than or equal to kappa universally bare in V. And to do that, because of a trick we talked about at the beginning of this presentation, we just need to have a generic G be any call omega kappa generic over V. And we just need trees such that the first tree projects to A, and the two trees project to complements in V bracket G. Okay, so this collapsing extension, V bracket G, is interesting. The set of reals in this extension is generic over HOD of V. And this is by that extended Vapenka's theorem result. That is, R of V bracket G is a set in V bracket G. And because our forcing call omega kappa is OD and homogeneous, that set is generic over HOD of V. So let H be generic over HOD such that the reals in V bracket G is the same thing as the reals in HOD bracket H. And here, because A is universally bare in HOD, we can pick trees T plus and T minus in HOD, which project to complements in HOD bracket H. But HOD bracket H and V bracket G have the same reals, so these trees T plus and T minus project to complements in V bracket G. And then there's one additional thing you have to do. You have to argue that the first tree T plus projects to A in V. So you have to work out the details for that, but it's relatively straightforward. Okay, so an interesting lemma. So if you have any UB set in HOD, you can stretch it to get a UB set in V. Oops. Now that proof is interesting, and it leads us to a definition we're going to use several times. So a set of reals A is called UB via OD trees, if and only if for every ordinal kappa, there are trees T plus and T minus in HOD, which witnesses that the set of reals is less than kappa universally bare. So said another way, UB via OD trees means the trees that witness that the set is universally bare can always be chosen to be inside HOD. And this proposition just kind of encapsulates the last slide, but it adds it adds the opposite direction as well. So let A be a set of reals. The following are equivalent. A is UB via OD trees, and that's equivalent to saying there's some UB set in HOD such that its reinterpretation in V is A. So the sets of reals that are UB via OD tree are precisely the reinterpretations of the UB sets in HOD. Okay, now we're ready for the upward theorem. So I believe this is folklore. Assume that HOD has a proper class of Wooden cardinals, then sigma 2, 1 UB statements are upward absolute from HOD to V. So we can do the proof. It's not too bad. Let phi be a sigma 2, 1 UB statement. So we can write it in this form. Let A be a universally bare set of reals in HOD that witnesses that this statement is true. And then let A star be the reinterpretation of A and V. By the previous result, this reinterpretation is actually universally bare in V. And then we just need the projective statement to be absolute between HOD and V. So we just need this part after the existential quantifier to be absolute. And this ultimately comes from L of AR absoluteness. Let me break that down just a little bit. So we have this A in HOD, and we have this A star in V. And what we can do this trick, we can let X be a set of ordinals that constructs the real numbers in V and also A star. But because X is a set, it's generic over HOD. So then by L of AR absoluteness between HOD and HOD bracket X, there's this elementary embedding. So there's this elementary embedding of the L of AR model of HOD into the L of A star R model of HOD bracket X. However, L of A star R of HOD bracket X is literally L of A star R because HOD of X contains all the real numbers of V and it contains A star. So you get L of AR absoluteness to deal with the projective part of the formula, and you're done. Okay, so that's the floor result. And note that it's interesting that, you know, it didn't matter if there was a proper class of Wooden cardinals in V. All that mattered was that there was a proper class of Wooden cardinals in HOD. Now, this L of AR absoluteness, as if you recall, you know, it's enough to assume a proper class of Wooden cardinals, but it also follows from closure properties of the UB sets of reals. So that we've actually shown a stronger theorem. We've shown if HOD satisfies that the UB sets of reals are closed under scales, sharps, and projections, then sigma 2, 1 UB statements are upward absolute from HOD to V. That'll be a little bit important later. So it makes sense at this point to make a conjecture. So assume that there's a proper class of Wooden cardinals in V, not in HOD, but in V. Then sigma 2, 1 UB statements are upward absolute from HOD to V. This is an interesting conjecture. You know, people can think about this. It seems to be a little bit tricky. So we don't know that if there's a proper class of Wooden cardinals in V, if this implies there's a proper class of Wooden cardinals in HOD. And let me just mention briefly that it seems that perhaps this has a little bit to do with the HOD conjecture. So what I mean by this is if there was an extendable cardinal in V and the HOD hypothesis held, then HOD would have a proper class of Wooden cardinals, and then you could therefore use the upward theorem. So said another way, if there was an extendable cardinal, but upward absoluteness of sigma 2, 1 UB statements failed between HOD and V, then the only possibility is that the HOD hypothesis is false in V. Okay, so there is this relationship to the HOD conjecture because, you know, kind of all our trouble goes away if we knew that HOD had a proper class of Wooden cardinals. And here's kind of a summary of the situation. So if there's a proper class of Wooden cardinals, we don't know if there has to be any measurable cardinals in HOD. And if there are not any measurable cardinals in HOD, that seems like a problem. It seems like it'd be really hard to get any kind of proof working without measurable cardinals in HOD. On the other hand, if there's an extendable cardinal in V, then HOD does have a measurable cardinal. This is by the HOD dichotomy. And if there's an extendable cardinal in V and the HOD hypothesis holds, then HOD has a proper class of Wooden cardinals, and then we're golden. Once we have that HOD has a proper class of Wooden cardinals, like I said, all of our trouble goes away. So I want to start talking about the downward direction. So that is, if a sigma 2,1 UB statement holds in V, then it holds in HOD, assuming that V has a proper class of Wooden cardinals. In order to really decipher what's going on in this situation, it makes sense for us to introduce the following definition. So a set of reals is called strongly OD if and only if both it and its complements have scales which are both OD and universally bare. Let me just be clear about that. So I'm saying that the set of reals has a scale which is simultaneously OD and universally bare, and the same is true about its complement. It seems like kind of a strange definition, but it's important for the theorem. So we're going to show very, very soon that if a set of reals is strongly OD, then it is UB versus OD trees. And a central question in this, in this topic is, if a set of reals is UB versus via OD trees, does it have to be strong OD? So that's a tricky question, and we'll come back to that later. Now let's talk about a couple simple things. If a set of reals is strongly OD, then so is its complement. And if a set of reals is UB versus OD trees, then so is its complement. Also note, you can show if a tree is UB versus OD tree, then it has an OD scale. Also, if a tree is UB versus OD trees, then it has a UB scale, assuming there's a proper class of Wooden cardinals in V. So UB versus OD trees sets have UB and OD scales, but we don't know if they have a scale which is simultaneously OD and UB at the same time, which is really weird. You think you could take the OD scale and the UB scale and somehow put them together, but it doesn't seem to work like that. So this lemma is just showing one of those arrows on the previous slide. This is a useful thing. Let's assume that the universally bare sets of reals are closed under scales, sharps, and projections. And let B be strongly OD, then B is OD versus, sorry, B is universally bare via OD trees. So the way this proof works is you start with B and let eta and C be scales for B that are both OD and UB, and let D be a universally bare set of reals such that B, eta, and C are elements of L of D, comma R. And then we're going to force over V using call omega kappa. And we could let B star, D star, eta star, and C star be the reinterpretations of these sets. Remember, these reinterpretations make sense because B, D, eta, and C are universally bare. By L of AR absoluteness, we have this elementary embedding. So because of elementarity, eta star and C star are scales of B star. Now, using eta star and C star, we can get trees in the extension that project to B star and its complement. And then we have to use a final trick. So we can actually get these trees to be ordinal definable in V bracket G. That's actually a slight lie. I don't know if they're literally ordinal definable in V bracket, but they almost are. They're ordinal definable using a ordinal definable parameter from the ground model. So it ends up being good enough. So you have these trees in the extension, and because they're sufficiently ordinal definable, you can pull them back to the ground model so that these trees are actually elements of HOD of V. So what have we done? We found trees T plus and T minus in HOD of V that project to complements in V bracket G, and it's not too hard to argue that T plus projects to B in V. Okay, so in summary, yes, every strongly OD set is UB via OD trees. We'll call this the tree stretching lemma. We need another ingredient for the downward theorem. So this is the so-called sigma 2,1 basis theorem. says if you assume ZF plus AD plus. By the way, AD plus is just an extension of AD. So if you assume ZF and AD plus, and if S is a non-empty collection of, oops, I think there's a typo here. S is a non-empty collection of sets of reals, which is sigma 2, 1 using a fixed set of reals B as a parameter. And if you have two scales phi and psi for B and its complement, then you can get some element of S, which is delta 2, 1 in the two scales. And maybe I should say it again. So if you have a non-empty sigma 2, 1 collection of sets of reals, then you can find an element of this, which is, delta 2, 1 in scales for B. I want to warn people that this result has been incorrectly stated a few times. So the way it was incorrectly stated is saying that the set of reals that you're picking is delta 2, 1 in B. That's actually false in general. So, but you can get your set of reals to be delta 2, 1 in the scales. All right, so we're ready for the downward. So assume that UB is closed under scales, sharps, and projections. Also assume that for every set of reals A, L of AR satisfies AD plus. So again, the hypothesis so far follows from a proper class of wooden cardinals. Let C be a strongly OD set of reals. And let phi of C be a sigma 2, 1 UB statement that uses C as a parameter. Then this statement is true in HOD using the parameter C intersected with HOD. Okay, so I want to talk a little bit about this proof. So you have this set of reals C, which is strongly OD. By the tree stretching lemma, it's UB via OD trees. So that allows us to kind of get our hands on it. And what we do is we fix some AD plus model, L of D comma R, where D is universally bare, that contains all the relevant sets. So it contains C and so forth. So let me back up a little bit. We have this sigma 2, 1 UB statement, phi, and we know it's witnessed by some UB set of reals A. But the challenge is A might be non-canonical. A may be really weird. We want to replace A with a logically simple set of reals. And that's where we use the sigma 2, 1 basis theorem. We work in the local determinacy model L of dr to apply the sigma 2, 1 basis theorem to take the witness for phi and replace it with a simpler witness. Now, in the same invocation of the sigma 2, 1 basis theorem, not only do we get a simpler witness, but let's also get scales for that witness and its complement. And you can argue that those two scales are both OD and UB. So now we have a witness for our sigma 2, 1 UB statement, which is strongly OD. And then we can use the tree stretching lemma again to get that witness is UB via OD trees. And there's one more ingredient. We have to deal with the projective part of the sigma 2, 1 UB formula, but we can deal with that as long as we have lots of scales kind of lying around, which we can use for the Tarski criterion. So when we use the sigma 2, 1 basis theorem, we should have also gotten scales to be used later for the Tarski criterion. Okay, so that's the basic idea, and it's a strange proof because, I mean, it uses the tree stretching lemma twice, actually. And, again, a big ingredient here is using the sigma 2, 1 basis theorem to drop down from a witness for our statement to a more logically simple witness. Oops. Now, something kind of odd about this whole thing is the definition of strongly OD is strange, right? Like on the previous theorem, you might think, why does C have to be strongly OD? Couldn't C just be UB via OD trees? And we don't know if the corresponding theorem is true, so we state it as a conjecture. So the downward conjecture is that the previous theorem holds, but for a parameter which is UB via OD trees. All right, why should we suspect that the downward conjecture is true? We might suspect it because there's actually an interesting equivalence which is going on here. So here's the equivalence. Assume there's a proper class of Wooden cardinals. The following are equivalent. Number one, HOD satisfies that its UB sets of reals are closed under scales, sharps, and projections. Note that that would happen if HOD had a proper class of Wooden cardinals. Two, every set of reals which is UB via OD trees is strongly OD. And three, the downward to HOD the downward to HOD theorem holds, but with UB via OD trees instead of strongly OD parameters. So our conjecture that the downwards theorem can be improved to just deal with parameters that are UB via OD trees, that's kind of justified by this equivalence right here. Okay. And something else which might seem kind of surprising that comes out of this equivalence is if the downward conjecture is true, then the upward conjecture is true. Because if the downward conjecture is true, then because of this equivalence, you get that if HOD has a proper class of Wooden cardinals, then, sorry, if let me say that again. If the downward conjecture is true, then because of this equivalence, if there's a proper class of Wooden cardinals, then HOD satisfies that its UB sets of reals are closed under scales, sharps, and projections. And then using that, you could get the upwards direction. Okay, so it's a little bit mysterious. It might seem like these things are not related, but they're all kind of like focusing on the same kind of idea here.
Dan,
Oh, yeah.
Can I just ask a quick question?
Yeah.
So it seems like so you're trying to at some places to make the assumptions as weak as possible, and so you're dropping down from a proper class of Wooden cardinals to just assuming for some of these results that the UB sets are closed under are very closed and stuff like that. But it seems to be like the key thing so I mean, if you want to reduce it even further, what you really need is this generic absoluteness result, right? That if you do some forcing, then you get this J from L of AR to L of A star R of the V of G, right?
That's a good point. Yeah.
So it seems like that is the optimal. that seems to be the key thing that you need, no?
I don't know if there's a way to get that, which is anything weaker than the closer under the UB sets of reals. But that's an interesting question. Like exactly in what situation do you have L of AR absoluteness? Yeah.
Okay.
Let me mention something else. It'd be really cool if you could show that if the UB sets are closed under those three operations, then they're closed under those operations in HOD.
I see. Okay. Yeah, sure.
And we don't know how to do that, but you know, it's related to the downward conjecture. I mean, yeah. Anyway, yeah. So if you could do that, then you could iterate this downward theorem. You could go from V into HOD, into the HOD of HOD, into the HOD of HOD of HOD, and so forth. So you could do kind of some kind of interesting argument like that. Anyway, yeah, you make a good point. It's like we really need L of AR absoluteness for some of these arguments. Okay. So that's it for downward absolute. What I'd like to do now is talk about a couple applications of this downwards theorem using omega logic. So if it's okay, I'd like to review some of the terminology from omega logic. So let A be a set of reals. Let M be a countable transitive model of ZFC. We say that M is A closed if and only if A intersect M is an element of M. And we say M is strongly A closed if and only if every set forcing extension of M is A closed. Now, I'm not sure if this terminology is totally standard. I think different authors have slightly different names for these things, so you just got to be a little bit careful about that. Okay. So omega logic uses this concept of omega provability, which is the following. Let phi be a pi2 statement. Let T be a theory. We write T omega proves phi if and only if there's a UB set of reals A such that every strongly A closed model of T satisfies phi. So so with omega logic, a pi2 statement is, a theorem if and only if it has some quote unquote proof, which is the universally bare set of reals. And you can also define omega logic not just for pi2 statements, but also for pi2 formulas that use real numbers as parameters. And to get this to make sense, you have to only consider countable transitive models M, which contain X. Otherwise, the models have no idea what X is, and the whole thing doesn't make any sense. But there is a way to make sense of this with real number parameters. On the other hand, if phi is a pi2 statement, then ZFC satisfies psi is a validity of omega validity of ZFC means that phi holds in every forcing extension. The omega conjecture says that omega provability and omega validity are the same thing, assuming a proper class of Wooden cardinals. But what you do have with, I think, just a proper class of inaccessible cardinals is if T omega proves phi, then phi is an omega validity of ZFC. So you have one direction with just a proper class of inaccessible cardinals. The other direction is the so-called omega conjecture. So who cares? So what's the point? The reason why I brought that up is because the notion of ZFC omega proving phi is a sigma 2(1) UB statement. So if V thinks that a pi2 statement is omega provable, then HOD agrees with that. And that's what this proposition says. If ZFC omega proves phi, then HOD also omega proves phi. Okay, so omega provability is downward absolute from V to HOD, assuming that V has a proper class of Wooden cardinals. Omega validity is upward absolute by a different argument, a totally different argument. The reason why omega validity is upward absolute is because omega satisfiability is downward absolute, and that follows by Vapenka's theorem. So omega provability is downward absolute, omega validity is upward absolute. You have those two things simultaneously. That tells you something about the omega conjecture. It tells you that assuming there's a proper class of Wooden cardinals and V satisfies the omega conjecture, then HOD also satisfies the omega conjecture as well. I should have probably had an extra slide just to show the arrows about that, but yeah.
Sorry.
Yeah.
So the omega conjecture says that if there is a proper class of Wooden cardinals, then these two things are equivalent?
Yes.
Okay, so if HOD doesn't have a proper class of Wooden cardinals in this situation, then it's vacuous?
Oh, okay.
Is this
That's
what
a
you
good.
mean?
That's a good question. I guess you could say. I mean, I guess you could get rid of the. I mean, yeah. So HOD might not have a proper class of Wooden cardinals, but the two things would be equivalent.
Okay. Okay.
That's a good point. Yeah. I want to mention another corollary of this downwards direction of omega provability from V to HOD. So basically what I want to try to say is if there's a proper class of Wooden cardinals and the omega conjecture holds, then HOD is some kind of core model in that it sort of absorbs the large cardinals from V. So I'll give an example using huge cardinals, although you could replace huge cardinals with like lots of different things here. So assume the omega conjecture holds and there's a proper class of huge cardinals, then HOD satisfies that every set is in an inner model with a huge cardinal. Now, note that, we don't know if the omega conjecture is really consistent with the proper class of huge cardinals, but, just pretend it is, right? Okay, so the way this proof goes is, you assume the omega conjecture holds, and assume there's a proper class of huge cardinals, and then Wooden has an argument using the omega conjecture that ZFC omega proves some kind of quote unquote large cardinal axiom. So there's an omega proof of some quote unquote large cardinal axiom, and that omega proof is downward absolute to HOD. So HOD thinks that there's an omega proof of the large cardinal axiom, and then by just the soundness direction of omega logic, HOD thinks that that large cardinal axiom is a validity, is an omega validity. So in particular, it thinks it's true. So HOD thinks that this large cardinal axiom holds, which is enough to get every set is in an inner model with a huge cardinal. Notice I didn't say what the large cardinal axiom is, but it's, something about, every set is in a transitive model with a huge cardinal, or something along those lines. It's like V is somehow closed under transitive models that contain these large cardinals. Anyway, I thought that was kind of interesting. So if you assume the omega conjecture, then HOD absorbs a lot of the large cardinals in V. I'd like to go on a slight tangent here and talk about mice. There's going to be a reason for that. So the following interesting lemma can be found in the paper, an omega logic primer. It says, let A be a universally bare set of reals. Then there's a universally bare set of reals A prime, such that whenever M is a countable transitive model of ZFC that is A prime closed, then M is A closed, and A intersect M is actually universally bare in M. Let people think about that a second. Okay, and I want to talk about omega-1 iteration strategies. So let M be a countable pre-mouse. When we talk about an omega-1 iteration strategy, sigma of M, we're always assuming that sigma is represented as a subset of R, or really a subset of bare space. We also want to make this convention that omega-1 iteration strategies always code the starting model. So what I mean by that is, if sigma is an omega-1 iteration strategy for a pre-mouse M, then whenever N is a countable transitive model of ZFC that is sigma closed, then that pre-mouse is an element of N. Okay. I also want to say that if you have a countable pre-mouse M, and if sigma is an omega-1 iteration strategy of M, then whenever N is a model which is sigma closed, then that iteration strategy intersected with N is actually an omega-1 iteration strategy for M from the point of view of N. So models which can see these, a model which can quote unquote see sigma realizes that it's an omega-1 iteration strategy for M from its own point of view. And the last thing I want to say about this mouse stuff on this slide is, if you have a pre-mouse, it has the universally bare omega-1 iteration strategy, then every real number in the mouse is actually in HOD. Okay. I'm just going to put this together in this proposition. This is where I was going with all this mouse stuff. Let M be a countable pre-mouse for which there exists a universally bare omega-1 iteration strategy sigma. Let X be a real in the mouse. Oops, that's a typo. The font should be a curly M. Then ZFC omega proves that X is in HOD. So the reals that are in mice are such that you can omega prove that they're in HOD. And there's a little proof here. It just kind of puts together the stuff from the last slide. If people can check this out afterwards if they're curious about that. But I mean, it just puts these ideas together from the last slide. Okay, for the last topic, I want to talk about what we could call super absoluteness. So we've been talking about sigma 2-1 UB statements, but if you want a more general class of statements, you could put a universal real quantifier in front. The statement that these more general statements are generically absolute, let's just call that super absoluteness. And you might wonder, do you have this type of absoluteness between V and HOD? And we're going to see that the answer is probably not. There's probably no, I mean, well, okay, I'll wait to say it until we get there. But yeah, you can wonder about this type of absoluteness between statements of this form. First, let's look at an example of such a statement. So let phi1 be the statement for every real number x. X is an accountable pre-mouse for which there exists a universally bare omega-1 iteration strategy. Is this statement really that form? Sure. It's like for every real x, it's unaccountable female. So yeah. Phi 1 implies that super absoluteness fails. Here's why. Assume that you have phi 1 holding in V, but add a Cohen real. Because adding a Cohen real is homogeneous, the HOD of the extension is contained in the HOD of the ground model, so that Cohen real you added is not in the HOD of the extension, therefore it cannot be in any mouse in the extension. So John Steele and Trevor Wilson have talked about the statement phi 1 a little bit in some of their papers. So phi 1 is great, but it's a little bit challenging because it's difficult to construct these mice. So because of that, there's a weaker statement, phi 2, which says the following: for every real number x, ZFC omega proves that x is in HOD. So by an earlier slide, when I talked about the reals in mice, it follows that phi 1 implies phi 2. So phi 2 is weaker than phi 1, but still, phi 2 implies that super absoluteness fails. And there's even a third weakening we want to consider. We want to consider phi 2, but replace ZFC with the theory ZFC plus there exists a wooden cardinal. So phi 2 prime is that weaker statement, and you can also show it implies super absoluteness fails. But the reason why phi 2 prime is relevant is because Wooden showed that the ultimate L axiom implies phi 2 prime. That is, the ultimate L axiom implies for every real number x, there's an omega proof that x is in HOD from the theory ZFC plus there exists a wooden cardinal. And let me just briefly remind people what the ultimate L axiom says. It says there's a proper class of wooden cardinals, and every sigma 2 statement holds in the HOD of some L of AR model for some universally bare A. Okay, so in summary, the ultimate L axiom implies this statement, which implies super absoluteness fails. And what does this have to do with absoluteness between V and HOD? Well, this is just another application of Wooden's work on the ultimate L axiom. So the proposition I want to talk about here is let LC be a large cardinal notion consistent with the axiom V equals ultimate L. Then even if HOD and V both satisfy this large cardinal axiom, you do not have absoluteness of these statements for all R sigma 2 1 UB between V and HOD. The proof is actually simple once you use all the machinery from the ultimate L. So the proof is just start with a universe that satisfies the ultimate L axiom, and then add a Cohen real. It turns out that the ground model is the HOD of the extension, and because you don't have this type of absoluteness between V and the extension, that means that the extension thinks this absoluteness fails between itself and its own HOD. Okay, so in summary, any large cardinal axiom consistent with the ultimate L axiom cannot imply this level of absoluteness. And that's my talk. Thank you. Thank you very much.
Well, thank you. Very interesting stuff. Okay, great. Are there any further questions or comments for Dan? Very interesting. I mean, one silly question maybe. So, I mean, when you started talking about the sigma 2 1 UB absoluteness, the first question that came to mind is like, what about pi 2 2 or UB or something like that? Is this definitely just inconsistent or?
Well, yeah, I had to think about that. But I mean, if you had an extra quantifier over universally bare sets of reals, I think you could easily turn that into an extra quantifier over just reals themselves.
Sure, yeah.
So I think
there is this stuff that it doesn't follow from anything, but I'm just asking, is it outright inconsistent if the first quantifier is a universal quantifier over UB sets?
That's a good question. I don't know.
Okay.
I mean, you know, if you have that if you have that the UB sets of reals are constructively closed, then then I think you would get that kind of absoluteness. Well, I'd have to think about it, but you know, so right, like if yeah, I'd have to think about it some more.
Okay. Okay. Interesting. Cool. So any more comments or questions? Okay. Well, it seems everybody is happy, and yeah, great talk. Thanks a lot.
Yeah, thank you so much.
Yeah, thanks, Dan.